Magnets have always fascinated scientists and enthusiasts alike, but what happens when a powerful neodymium magnet interacts with a copper sphere? Will it float? Will it fall? Or will it defy gravity in a way that seems impossible? This experiment explores the mysterious interaction between magnetic fields and conductive metals, particularly how if you've ever been amazed by magnets sticking to metals, you might be surprised to learn that copper isn't even magnetic. So why does a magnet react with it at all? The answer lies in the principles of electromagnetism, Lenz's law, and eddy currents, which we will explore in detail. Let's dive into the science behind this fascinating experiment, see what happens when a super strong magnet is dropped into a copper sphere, and uncover why it seems to float instead of falling freely. Neodymium magnets are one of the most powerful types of permanent magnets known to science. Made from neodymium, iron, and boron, NdFeB, these magnets generate incredibly strong magnetic fields, far greater than ordinary ferrite or ceramic magnets. Extremely strong, they can attract objects from a significant distance. Permanent magnetism, unlike electromagnets, they do not require electricity. Brittle nature, despite their strength, they are fragile and can break under impact. High conductivity, they interact strongly with metals that conduct electricity. These properties make them perfect for our experiment, where we test how such a strong magnet interacts with a non-magnetic but highly conductive material like copper. Copper is a non-magnetic metal, meaning it does not attract or repel magnets directly like iron or steel. However, it is one of the best conductors of electricity, which plays a crucial role in this experiment. Excellent electrical conductivity allows electric currents to flow easily. Non-magnetic. Unlike iron, it does not generate its own magnetic field. Soft and malleable, can be shaped easily into spheres or tubes. Since copper doesn't attract magnets, you might think that dropping a neodymium magnet into a copper sphere would have no effect. But the reality is far more surprising. When a neodymium magnet is dropped into a copper sphere, it doesn't just fall freely like a normal object. Instead, something fascinating happens. It descends slowly, almost as if it is floating in midair or experiencing resistance. This strange behavior is caused by electromagnetic induction, a fundamental principle of physics described by Lenz's law and eddy currents. According to Lenz's law, whenever a changing magnetic field passes through a conductor, like copper, it induces an electric current in the conductor. These electric currents are called eddy currents, and they create their own magnetic fields. Eddy currents explained, as the magnet moves, its magnetic field changes inside the copper. This change in magnetic flux induces circular electric currents in the copper. These currents generate their own magnetic fields, which oppose the movement of the falling magnet. This opposition creates a magnetic braking effect, slowing down the magnet's fall significantly. Now that we understand the science, let's see the experiment in action. A powerful neodymium magnet, a copper sphere, hollow or solid, large enough to fit the magnet, a camera for slow magnetic stand or setup to drop the magnet freely. Ensure the copper sphere is smooth and clean for a clear observation. Hold the neodymium magnet above the sphere and get ready to drop it. Drop the magnet into the center of the copper sphere and observe what happens. Unlike a normal object, the magnet does not fall instantly. It moves slowly, as if defying gravity due to the eddy current effect. If you record the drop in slow, you can see how much the fall is delayed. Although the magnet falls much slower than normal, it doesn't float forever. This is because Lenz's law only opposes motion. It doesn't create upward force. Over time, gravity still pulls the magnet downward, but at a much reduced speed. However, if the experiment is done inside a copper tube, the effect becomes even more dramatic. The longer the tube, the slower the magnet falls. To explore this effect further, you can try different variations. 1. Using different materials. Try aluminum or brass instead of copper. 2. Changing magnet strength. Use a weaker or stronger neodymium magnet. 3. Altering the sphere shape. Try a tube instead of a sphere for longer travel time. 4. Testing with liquid copper. Drop a magnet into molten copper and observe. Each variation changes the interaction and helps us understand electromagnetic principles better. This magnetic phenomenon isn't just a cool experiment. It has real applications in technology and engineering. Magnetic braking systems, used in roller coasters, trains, and elevators to provide smooth stopping power without physical contact. Eddy current testing, used in metal inspection and non-destructive testing for quality control. Magnetic levitation, maglev trains. These use similar principles to reduce friction and increase speed. Energy generation. Eddy currents play a role in induction heating and power generation. Understanding these effects allows scientists and engineers to develop advanced technology based on electromagnetic physics. The experiment of dropping a neodymium magnet into a copper sphere is an amazing demonstration of Lenz's law and eddy currents. Watching a magnet defy gravity and fall slowly instead of dropping freely challenges our everyday intuition and highlights the incredible invisible forces of electromagnetism. Whether you're a science enthusiast, student, or DIY experimenter, this is a must-try experiment that perfectly illustrates how physics shapes the world around us.